Hi everyone, and welcome to lesson 2.2, where we're going to discuss distributions of sample proportions, which is a continued discussion from 2.1. In the last lesson, we did a Reese's Pieces activity, and everyone should have calculated the proportion of the sample that was orange. And what we saw was that every person in the class had a different sample, and each had different sample proportions. Remember, your sample proportion was p hat, and we obtained p hat from our larger population, p, and p in that case was all Reese's Pieces. P hat is our sample statistic, okay, and P is what we call our population proportion. So that's our sample proportion. What I'd like you to do is take a minute and pause the video and read through this paragraph and review what we talked about in the last section. You're going to be filling in the blanks, and you have some choices in parentheses. So you're either filling in for this first blank, P or P hat, and so on. So pause the video and then we'll come back and review. Given a population and a specific trait that the members of the population may or may not have, we are interested in the proportion of the population having the trait. The proportion of the population having the trait is denoted by the symbol P. When the population is so large that we can't survey all of the members, we take a random sample. The proportion of the random sample is denoted by the symbol P hat. If many random samples are taken, we get many sample proportions, and the collection of sample proportions is called the sampling distribution of p hat. And that's really important because we're going to be looking at that over and over again as we are investigating problems in the rest of the chapters. So again, when we take random samples and we get many sample proportions, that collection of sample proportions is known as the sampling distribution of p hat. And if you recall, what happened was we created a dot plot and we had all of our sample proportions and they were all kind of piled around the center, which we estimated to be our true population proportion. So p hat, if we take a good sample and we do things correctly, should help us estimate P, which is your population proportion. The sample proportions pile up around the mean of the sampling distribution, which is equal to P. So here is your, think of this as your dot plot with all your P hats. We assume, since that's the center, that P, which is our population proportion, should be in that center, and that sampling distribution of P hat is used to approximate P, your population proportion. The sample proportions vary, as we saw. Not everyone had the same sample. Even though you had 20 Reese's Pieces each, the color distributions were not the same. The typical difference between the sample proportion and the population proportion is described by the standard deviation of the sampling distribution. The formula for the standard deviation is going to be the square root of P times 1 minus P divided by N, which is your sample size. And that's the square root of that. Another name for the standard deviation of the sampling distribution is the standard error. And the error is not an error as in a mistake, but it's because we are approximating the standard deviation based on our parameter that we've calculated through our sample proportions. So we may not know our true standard deviation, but we are approximating it from our p hat sampling distribution. So in the last lesson, some of you may have gotten the impression from using that applet that the sampling distribution is always approximately a normal distribution, but that is not always the case. So here's 3 different p hat sampling distributions, And we're also provided the corresponding p, so the proportion, the population parameter, and also n, which remember is your sample size. So all of the sample sizes are 20, but as you can see, each of the parameters is different. And not all of the distributions are shaped normal. So which of the three distributions is the normal distribution not a good approximation? If you're looking at figure 1 and figure 3, for those two distributions, the normal distribution would not be a good approximation. So how can we verify whether or not the normal distribution can be used as an approximation of the p-hat sampling distribution? We're going to make some assumptions, and assumptions you can't really know whether they're true or not, but you can check certain conditions to see whether the data was collected in a way that the assumption is reasonable to make. The first assumption we're going to make is called the independence assumption, which just says the individuals in the sample must be independent of one another. So in other words, with your sample of Reese's Pieces, each of those candies was independent of one another. You having an orange candy in there didn't affect having another orange candy or a brown or a yellow. Okay, we're going to check that using these two conditions, the randomization condition and the 10% condition. So you're going to see this theme of randomization throughout the book. The randomization condition says that the sample must be randomly selected. So you have to make sure that the sampling method is not biased, and or taking a random sample will help eliminate or avoid bias, which once you have bias in a sample, you can't remove it, and then it distorts your conclusion. So you're going to make sure the data are representative of the population. A lot of times it'll say in the problem that the sample was randomly collected or a random sample of 20 people. If they don't say random, just make sure that the data represents the population. Okay, so if I'm dealing with, if I'm testing a certain product, like let's say shampoo, and my sample is all females, that's not really random because I don't know how the shampoo would affect male hair. So I would want to make sure that I have males and females and that all genders are accounted for to be representative of the population. You also want to look at the 10% condition. So sampling too much of a population can be a problem. The sample should represent no more than 10% of the population. So sometimes we don't know the actual size of the population. In fact, it's very rare to know the size because populations change frequently. We need to determine whether it's reasonable to assume that our sample represents no more than 10% of the population. So if you think back to the Reese's Pieces activity we did, we don't know the population of all Reese's Pieces, but we do know that the sample that you had was no more than 10% of that population, okay? So what we would do is just use a little math here, and we're going to calculate 10 times n, which is your sample size. So our sample size was 20. 10 times 20 would be 200. Okay, so it would be reasonable for us to assume that the population of all Reese's Pieces is greater than 200 Reese's Pieces, okay, or 10 times the sample size, or you can just think of it as 10n. The second assumption we make is about the sample size, n, and it has to be large enough. So this depends on the value of p, okay? The closer it is to 0, from 0 to 1, the larger n needs to be. So we're going to check the following condition. We're going to look at the what's called success-failure condition, which says the sample size must be large enough to ensure that we can expect to see at least 10 successes and 10 failures. So think of the successes as P, and failures is sometimes referred to as Q, but your book refers to it as 1 minus P. So here's the criteria that we're going to check for using the normal approximation for the p-hat sampling distribution. We're going to make sure the sample is randomly selected, the population should be greater than 10 times the sample size, or 10n, and both n times p, which is your success, and n times 1 minus p, which is your failure, need to be at least 10. So we have to make sure that they are greater than or equal to 10, or in other words, 10 or more. Okay. So if we check the three cases shown previously, we're going to state which ones satisfy the third condition. So if we check these three cases, okay, which ones would satisfy the third condition? And that would be assumption number 2, which is where we want to do the success failure. N times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. If we look at our distributions here, we can see that we know that our sample size for all of them is 20, okay? So depending on what the population is, we would have to assume that the sample size is no more than 10 times the population, and we would want to be sure that these data values were chosen randomly, okay, so it's a random sample, and then we would also need to know p and n times 1 minus p, which we do know because p here is 0.05, so if we multiply 0.05 times 20, so if you pull up, you don't really need a calculator for this, but 0.05 times 20 is 1, and 1 is not greater than or equal to 10. So therefore, that third condition, the success failure condition, does not apply to that first case. However, when I check the second one, if I take 0.5 times 20, I get 10, and 10 is equal to itself. So the success failure condition does apply, and it would apply for figure 3 as well. The only things we don't know about these three figures is whether the samples were randomly chosen, and also what the population would be, because there's no context here, so we can't determine the 10% condition. All right, so let's look at an example here. If you want to pause the video, that would be a good idea, and then we'll do it together. The millennial generation is the people who are 18 to 29 years old, although that would be a little different now. And the Pew Research Center has written a report comparing this generation with other generations like Gen X and the baby boomers. One of the lifestyle differences was the percentage of tattoos. 38% of the millennials had at least one tattoo, but only 15% of the baby boomers did. Suppose random samples of 500 millennials are taken, and the proportion of the sample having a tattoo is recorded. We want to complete the sentence describing the meaning of the symbol P in the context of this problem. Okay, no numbers, so it's very important to be able to define and understand what P is. So in this problem, P is the proportion, okay, or population proportion, okay, as opposed to the sample proportion of all millennials who have a tattoo. Okay, based on this problem, what would be the numerical value of P? So if I look at the problem, I can see that 38% of millennials had at least one tattoo. So P here, since it's the population proportion of all millennials who have a tattoo, would be 0.38. Okay, so we want to find the mean and the standard error of the p-hat distribution. So the mean of the p-hat sampling distribution in this case, remember, it's going to be the same as the population proportion, or close to it. So here, it's going to be whatever p is, which is 0.38. So to find the standard error, which again, remember, is just the standard deviation, okay? It's just called that because we don't have the standard deviation, so we're kind of estimating it. The standard error of the p-hat sampling distribution would be calculated in this way. So we would write the standard error of p-hat is equal to the square root of p, which is 0.38, times 1 minus p, and then we're going to divide by the sample size, which was 500. Okay, and we're going to have to do some calculator work there. So let's pull up our calculator and let's type this in. So I want to do a square root, so I'm going to hit the second button and then the x squared. Okay, I have square root. And then I'm going to put double parentheses here. I'm going to do 0.38, okay? And then I also want to put 1 minus 0.38, okay? Now, the reason we're putting double parentheses is because I want the calculator to know I'm multiplying 0.38 times the 1 minus 0.38, but then I want to take that whole expression and divide that by 500. And when you hit enter, you get 0.0217. So we'll round to 4 places. That is our standard deviation or standard error. Okay, so let's verify that the normal distribution criteria are met. We're going to check the 3 conditions and we'll show any calculations we need to. So if you'll remember, the first condition was that it needed to be a random sample. So all we really need to do is look in our problem for the word random. And it does say a random sample of 500 millennials. So that's good enough to satisfy that condition. So we're going to write that down. Okay, condition 2 was we needed to check the 10% rule, right? So we need to take the number 10 and multiply it by our sample size. Our sample size is 500. And when we do that, we get 5,000. So what we want to do is make sure that our population of millennials is not greater than, or that our sample size is not greater than 10% of the population. So we know that there's way more than 5,000 millennials, right? So we're good for that. So we could put something like our population of millennials is greater than 5,000. And then the last thing we want to check is what's called our success failure. So remember that's your n times p, and it has to be greater than or equal to 10. And your failure is n times q, or n times 1 minus p, which must also be greater than or equal to 10. So n here is 500, that's our sample size, and p is 0.38. And we just need to calculate and make sure that that's greater than or equal to 10, okay? So we're gonna go here and multiply 500 times 0.38, and we get 190. So 190 is greater than or equal to 10. You could also do 500 times 1 minus 0.38, or another way you could get that number is just subtract 500 minus 190. So we know that that would be like 310, which we also know is greater than or equal to 10. So all 3 of our conditions are satisfied. Okay, so therefore we can verify the normal distribution can be applied here. So I'm just going to write, since all 3 conditions are satisfied, we can apply the normal distribution criteria. Okay, so in other words, we can assume that if we were to graph this distribution, it would be normally distributed. So let's see what that would look like. Okay, we're going to sketch our normal model. And remember that in the center is your mean, and your mean here is P, which is 0.38. And we're going to graph 2 standard deviations, 2 or 3 out. It doesn't really specify here, so let's do 3 out in either direction. So in order to get those other values, remember that your standard error was 0.0217. So let's write this down here. We've got our normal model with our mean is 0.38, and the standard error was 0.0217. So all we're going to do is add 0.0217 to 0.38, and we're going to keep doing that to get all those values. So in other words, I have 0.38 plus 0.0217, okay, which is going to give me 0.4017. So that number right here is 0.4017. And then I'm going to add 0.0217 again, okay? Now, if the numbers are getting too big, you can just kind of estimate there, okay? So we're going to keep doing that. So 0.4017 plus 0.0217, and we get 0.4234. So basically it's counting by twos, okay? And then I'm going to go backwards, and I'm going to do 0.38 minus 0.0217. And I get 0.3583, so it's like basically 0.36. Okay, and then 0.34, and then 0.32. So we want to label, which we did, the mean. Okay, our mean is right in the center. So this is important. Okay, here's our mean. And we also labeled 3 standard deviations out. Okay, so remember, we could apply the empirical rule, which tells us 68% of the data falls within 1 standard deviation of the mean, 95% would fall within 2 standard deviations, and 99.7 would fall 3 standard deviations. If a random sample of 500 millennials had 200 with a tattoo, what is the sample proportion p hat? So in your sample of 500 millennials, we know n is 500, and we counted 200 with a tattoo. So our p hat is 200 divided by 500, which is just 0.4. Okay, so 0.4 would go right here. It's actually right, kind of right on our normal curve there. Remember, that number was estimated a little bit. Okay, we rounded. Okay, we want to find the probability that a random sample of 500 millennials will have a proportion higher than 0.40. Shade the appropriate area in the sketch you made and show the calculations. So here we want to find this area, okay, higher than that. And we're looking for the probability, which remember, it means the same thing as percentage, proportion, area. They all mean the same thing. So how do we do that? What we need to do first is find the z-score, okay, which will be easy here if we round. So we have our value minus our mean divided by the standard deviation. So when we do that, we get, let's see, so 0.40 minus 0.38, put it in parentheses, and then divide by 0.0217, and we get 0.9217. Okay, which basically is just a z-score of 0.92. So now I want to find the probability that z will be greater than 0.92. And remember, to do that, we're going to use our normal CDF. So we need to get on the calculator, and normal CDF is under second vars, and you're going to pick number 2. And our lower bounds, so let's look at our picture again. Our lower bound here would be the flag. Okay, so bound is boundary. And the flag has a z-score of 0.92. So we know that that's going to be our lower bound. Okay, our upper bound is infinity, but we can't write that, so we're just going to use the number 100 because that's a high enough z-score that it won't make a difference. So we're going to have 0.92, 100, and then remember the mean stays 0 and the standard deviation stays 1 because we're looking at our standard normal model. And then all we have to do is just calculate that and it'll give us the area. So let's type in these numbers, 0.92, comma 100, comma 0, comma 1, and then hit enter, and we get 0.1788. So that is our proportion of millennials that would, if you were to select a random millennial, the probability that they would have a tattoo is approximately 17.88%. You could also say the proportion of millennials in a random sample that would have a tattoo is 0.1788. Okay, so let's fill in this sentence here. And right now you're guided to write these sentences a specific way, but in the future you're gonna have to get used to interpreting your results. Okay, so the probability is 17.88%, we're about 18%, that a random sample of 500 millennials will have more than 200 people with a tattoo. So in context, that is what we just found. And that's it for the lesson. The rest is homework problems. Please take the time to do these problems. It will help you with the future topics that we're going to discuss. Enjoy the rest of your day. If you have any questions, please let me know. The speed limit on a road in town is 35 miles per hour, and a device used to measure the actual speed of cars traveling on the road finds the distribution of speeds to be approximately normal, with a mean of 35 and a standard deviation of 5. Answer the following questions using the empirical rule. So we want to label the normal curve below with the appropriate mean miles per hour and 3 standard deviations in either direction. Okay, and that's generally going to be the rule that we're going to follow for the remainder of the course. We want to, let's see, answer the following questions using the empirical rule. So we want to then, below that scale, label the speeds with the appropriate z-scores as you did in question 20. All right, so if we look at the problem, they tell us that we have a mean of 35 and a standard deviation of 5. So remember that this is actually mu and this is sigma. Okay, mu is, again, the population average or population mean. Okay, so you're taking into account all these cars whose speed was taken. So that's your population. And then we found the standard deviation as well. It was given to us in this problem. This is our population standard deviation of 5 miles per hour. Okay, so we know that the mean goes in the middle because it's the average. So 35 is going to go in the middle. And since my standard deviation is 5, I'm going to add 5 to 35 and I would get 40. And that represents 1 standard deviation above the mean. Okay, 35 minus 5 is 30. That would be 1 standard deviation below, and so on. Okay, I'm going to go back to the mean. 35 plus 5 gives us 40. 40 plus 5 is 45. 45 plus 5 is 50. So this is 2 standard deviations, 3 standard deviations. And if I go backwards, I'm just going to subtract 5 each time. So we know that this 25 miles per hour is 2 standard deviations below, and 20 miles per hour is 3 standard deviations below. So there's my normal distribution set up according to this problem. And by looking at it, I know that my mean is 35, and these are your z-scores. If you're a car that's traveling 40 miles per hour, right, you are 1 standard deviation above the average speed. Okay, so these represent the z-scores. Okay, so that would just mean z equals 1, and this means z equals -1. So if you're a car and you're traveling 30 miles per hour, you're actually 1 standard deviation below the average speed of the cars on that road. So then answering these questions, what is the probability that a randomly selected car on this road is traveling below 25 miles per hour? So think of this right here is our 25, and I'm going to put a little flag right here. We want the probability that any car randomly selected, right? So any car would have an equal chance of being chosen, that car is traveling below 25 miles per hour. So I need to use my empirical rule to figure that out. So if you'll recall, anywhere from 25 to 45 is 2 standard deviations above and below the mean. And using the empirical rule, we know that that area in between the two flags is 95%. So if I take 100% and subtract that 95%, it's going to leave me with this area and this area. So in other words, if I do 100 minus 95, I'm really subtracting away this piece right in here. So it's going to leave me with 5%, right? But that represents either side of the flag. We only care about this side. So I need to divide by 2 because remember, one of the properties of the normal distribution is that it's symmetric. It's the same on both sides. So these flags are the same distance from the center. So I'm just going to do 100% minus 95%, which gives me 5%. And then I'm going to have to make sure I take the 5 and divide by 2, which is 2.5%. So the probability that a randomly selected car is traveling below 25 miles per hour is actually just 2.5%. Now I want to know, what is the probability that a randomly selected car on this road is traveling between 35 and 40 miles per hour? Okay, so I'm going to take this this picture here, and I'm just going to copy paste. Okay, I'm going to shrink it down, and I'm going to, let's see if this will work. Let me put that back a second. Let's see. Okay, instead of redrawing, I can just go like this, and then maybe I can erase that stuff. Okay, so I'll do the best I can getting rid of this stuff. All right, I don't want to mess with it too much, but hopefully you can all see now. So now I'm looking for 35 and 40 and in between, right? So let me use a different color here. So 35 is here and 40 is here. And there's a couple ways you could do this, okay? So one way that stands out is, if you'll remember, between here and the furthest orange flag, so here, that's 68% of the data. It falls within 1 standard deviation. But I'm only looking for the probability that someone traveling on that road is going between 35 and 40 miles per hour. So using one of the characteristics of the normal model, I know that it's symmetric. So all I would have to do is divide this 68 by 2, because this area is the same as that area. And 68 divided by 2 is 34. So approximately 34% of cars traveling on that road will be traveling between 35 and 40 miles per hour. Okay, we know that the middle 95% of cars are going to be 2 standard deviations above and below the mean. So we know they're going to be between 25 and 45 miles per hour. And almost all of the cars on this road would be traveling between 20 and 50 miles per hour. Anything beyond those two values is extremely rare. In this book, we say anything above 2 standard deviations is rare. So the probability that someone is driving more than 45 miles per hour on that road would be rare. And the probability that someone is traveling less than 25 miles per hour would be rare. So if you think about it, anybody going above 50 or below 20 would be extremely rare. So mostly everybody, 99.7%, are traveling between 20 miles per hour and 50 miles per hour. The reason we can't say 100% is because, remember, the whole curve represents 100%. So that's the end of this lesson. We're going to see more of the normal distribution throughout the entire book. So it's really important, this section, that you understand z-scores and also the normal distribution. So please go back over the notes and go over the summary here. These are highlighting the important things that you need to know. And then there's the homework at the end. This is the bare minimum of practice that you should do to feel comfortable with this section. If you need more practice, I can provide more problems for you to try. But doing these problems is, again, the bare minimum. If you've never seen this before and you need practice doing it, because a lot of what we're going to do going forward will relate to z-scores and the normal distribution, and your understanding of it is critical to understanding the rest of the course. So please reach out to me if you have any questions, and I hope you all enjoy the rest of your day.